What is nuclear fusion? Nuclear fusion is the process in which two light atomic nuclei combine to form a heavier nucleus, releasing a large amount of energy. Fusion is the energy-producing process that powers the Sun and the other stars. On Earth, the most promising fusion reaction involves isotopes of hydrogen, namely deuterium and tritium, producing helium and energy. Scientists are developing fusion reactors to harness this energy as a future source of electricity. Why nuclear fusion as a sustainable energy source? Clean energy potential fusion produces no carbon dioxide during operation, making it an environmentally friendly energy source. Abundant fuel supply deuterium can be extracted from seawater, providing a nearly limitless fuel source. Future energy security. As global energy demand continues to increase, fusion has the potential to provide reliable and sustainable electricity for future generations. Next is connection to modern physics. We have three. The first one is nuclear physics. Fusion involves interactions between atomic nuclei and the conversion of mass into energy. The second one is electromagnetism. Magnetic confinement devices such as tokamaks use powerful magnetic fields to control plasma. The last one is materials science. Developing materials that can withstand extreme temperatures and radiation is a key challenge in fusion research.
To structure my independent learning path for these PHY310 topics, I executed a systematic 4-step methodology. Firstly, we did a literature review using peer-reviewed paper from the IAEA and scientific journals to ensure technical accuracy. Second, also we use multimedia resources like technical lectures and website research of the ITER facility to help visualize the complex reactor geometries. Third, I cross-reference data by comparing results from different facilities, especially the National Ignition Facility (NIF) and Joint European Torus (JET). Finally, I using a mapping concept to break down abstract plasma confinement theories into the visual structure you see in this presentation. The primary challenge encountered during my independent learning process was a high level of technical complexity inherent in plasma physics. Mastering concepts such as magnetic confinement and plasma stability required a steep learning curve. To overcome this, I refer foundational physics website to firmly secure my understanding of the core mechanics before moving on to the complex research paper, mapping out the theory systematically to ensure conceptual clarity. Secondly, a major hurdle was distinguishing between sensationalist media hype and actual scientific reality. Many commercial news sources tend to exaggerate nuclear fusion timelines. In order to maintain academic integrity in my research, I filter out non-verified reports by focusing strictly on quantified Q values, which is representing net energy gain, and anchor my findings entirely to empirical laboratory data from established fusion test facilities. Finally, managing an overwhelming abundance of information online within my self-directed learning hours proved challenging. To tackle this information overload efficiency, I implement an information which is filtering strategy by prioritizing official reports and publication from recognized global bodies such as the International Atomic Energy Agency (IAEA). This approach ensures that all breakthroughs cited in my presentation are highly credible and verified by scientific community.
Hi, I will explain about the intellectual proficient in presenting modern physics concept, law, and theories. What is nuclear fusion? Nuclear fusion is a process in which two light atomic nuclei combine to form a heavier nucleus, release a large amount of energy. In this reaction, a deuterium nucleus and tritium nucleus fuse to produce a helium nucleus, a neutron, and 17.6 MeV of energy. The most commonly studied fusion reaction on Earth involve the isotope of hydrogen, deuterium, and tritium. There are two principles of modern physics. First is S-time mass, energy equivalent, which is E equal to mc squared. The second one is quantum tunneling. Positive nuclei usually push each other apart, but quantum mechanics allows them to overcome this barrier, so fusion can occur even when it seems impossible according to classical Physics. There are some important of nuclear fusion on Earth. First, produce enormous energy output from small amount of fuel. I got one example, which is one uranium fuel pellet the size of a fingertip produce as much energy as 1 ton of coal. The second one is low greenhouse gas emission. The third one, abundant fuel supply as deuterium can be extracted from seawater. Other than that, safer than nuclear fission with no risk of runaway change reaction. The other one could provide continuous baseload electricity, unlike solar and wind energy, which is depend on weather condition. Last one, it can generate less long-life radioactive waste compared to conventional nuclear power plants.
For now, we move to factual details of nuclear fusions. Fusion reactions occur at extremely high temperatures, typically above 100 million degrees Celsius, where matter becomes a state called plasma. Fusion reactors use only small amount of fuel at a time, which reduces risk related to fuel storage and transportation. Fusion energy has the potential to meet growing global electricity demand while reducing dependence on fossil fuels. Next, we move on how nuclear fission as a sustainable energy source is applicable in daily life. Nuclear fission can improve daily life by providing a clean and reliable electricity for homes, schools, hospitals, transportation, and industries. It can support electric vehicle, reduce air pollution, and help meet future energy demands while promoting environmental sustainability.
There are some recent advancements and a controversy about the fusion. First, progress in ETER. The ETER project in France is currently the world's largest fusion experiment. Scientists and engineers from multiple countries are developing a Tacoma reactor capable of sustaining fusion plasma for a long period. ETER aims to demonstrate that fusion can be used on an industrial scale to generate electricity. The second one is ignition achievement at the National Ignition Facility, which is NIF. In December 2022, scientists at the NIF achieved a historic milestone called fusion ignition, where a fusion experiment produced more energy from the fusion reaction than the laser energy delivered directly to the full target. This achievement demonstrates that controlled fusion can generate net energy gain under laboratory conditions and mark a major breakthrough in fusion research. There are also many controversy and challenge to make this experiment. First, high cost. Fusion research require extremely expensive facility, superconducting magnet, and advanced material. Critics argue that fusion projects consume large amount of funding while commercial development remain uncertain. The second one, commercialization timeline. Some experts believe commercial fusion power could become available within the next few decades, while others argue that significant technical obstacles may delay widespread development much longer. This debate continues within the scientific community. The third one is tritium availability. Many fusion reactors rely on tritium fuel, which is scarce and radioactive. Developing sustainable tritium production system is essential before large-scale fusion power plants become practical.
Today, I would like to talk about the significance of continuous self-development in achieving success in nuclear fusion. As we know, nuclear fusion is one of the most promising energy technologies for the future. However, it is also one of the most challenging scientific fields. Because of this, professionals involved in fusion research must continuously improve their knowledge and skill to keep pace with new development. First, continuous self-development helps scientists stay updated with emerging technologies. Since nuclear fusion is rapidly evolving, researchers must constantly learn about new discoveries, reactor design, and plasma technologies. For example, scientists working on the ITER project continuously expand their knowledge to improve reactor performance. Secondly, it helps development advanced technical skill.
Fusion research combines physics, mathematics, programming, and engineering. Learning tools such as Python or MATLAB allow researchers to analyze plasma behavior and process large amounts of experimental data more effectively. Next, the third one is self-development strengthens problem-solving and critical thinking abilities. Fusion research involves complex challenges such as maintaining plasma stability and improving energy efficiency. Through continuous learning, scientists can develop innovative solutions that bring fusion energy closer to reality. Finally, continuous self-development opens doors to greater career opportunities. Professionals who actively improve their knowledge and skill are more competitive and better prepared for leadership roles and international research collaboration.
So now, I would like to present about potential career paths in nuclear fusion. Nuclear fusion is a promising future energy source that produces clean and sustainable power. As this technology develops, many exciting career opportunities are becoming available. First, we have research and scientific roles. One example is an experimental plasma physics. Their job is to study how plasma behave inside fusion reactor such as tokamaks. They focus on heating, confining, and stabilizing the plasma to achieve net energy gained. Another important role is a computational physics. They develop advanced mathematical model and computer simulation to predict plasma behavior and reduce turbulence in fusion reactor. The second category is energy engineering and technical roles. A superconducting magnet engineer designs powerful high-temperature superconducting H2S magnets. These magnets create strong magnetic field that help contain the plasma safely. Next, a nuclear material engineer develops new material for reactor walls. These material must withstand extreme temperature and continuous neutron bombardment over long periods. There is also the rules of a control and AI engineer. They use artificial intelligence and machine learning to monitor and adjust magnetic fields in real time, helping to prevent reactor disruptions and improve efficiency. And finally, there are policy and commercial roles. A fusion regulation specialist is responsible for developing safety standards and licensing framework for fusion technology. These regulations are different from those used in traditional nuclear fusion. Another area is an energy market analysis. They study how future fusion work plants can be integrated into electricity grids and evaluate their economic impact on the energy market. So now, let's hear about key challenge and development strategy in the nuclear fusion industry. Although nuclear fusion has a great potential as a clean energy source, there are several challenges that need to be overcome. The first challenge is a long development horizon and commercial uncertainty. The reality is that fusion technology is progressing rapidly. However, achieving full commercial and grid-ready fusion power plant will still require several more years of intense research, testing, and development. To address this challenge, a useful development strategy is to build a dual-purpose skill set. Besides having a strong background in physics, students and professionals should also develop transferable skills such as advanced data analytics, high-performance computing, or cryogenic engineering. Their skills are valuable both within and outside the fusion industry. The second challenge is the interdisciplinary nature of fusion technology. Fusion projects require experts from many fields to work together, including plasma physics, material science, electrical engineering, and computer modeling. Such successful collaboration is essential because no single discipline can solve all the challenges alone. To prepare for this environment, individuals should aim to become T-shaped professionals. This means having deep expertise is one area while also gaining knowledge of related disciplines. Doing so helps improve communication and teamwork across different scientific and engineering fields. The third challenge involves balancing academic qualification with industry needs. Traditionally, fusion research has emphasized the importance of pursuing a PhD and conducting theoretical research.
However, many private fusion companies are currently looking for engineers and programmers who can develop practical hardware and software solutions immediately. A good strategy is to choose an educational path that matches your career goals. If you are interested in scientific discovery and research, pursuing a PhD may be the best option. On the other hand, if you prefer hand-on engineering works, practical internship, specialized master program, and laboratory experience can be more beneficial.